Hey there, folks. Can you guys hear me? Wonderful. Oops. Okay. All right, folks, my clock reads 12, so let's go ahead and get started. Welcome to the first of a couple of weeks of entirely remote classes. I tried this out yesterday. It seemed to work mostly okay, so we'll see how it goes today. There's a lot of material to get over today, so I'm going to not spend a huge amount of time right at the beginning with announcements. I have posted a what to expect the rest of the semester post to Piazza that goes through on a day-by-day basis what's supposed to be going on. So the main things are that because of all of the meetings I have had to have over Thanksgiving break and continuing on into this week due to the Chegg cheating on the previous exam, I have not been able to put together content videos moving forward. And so I will be doing live lectures on the normal Mondays and Tuesdays. If any of the content doesn't get covered in those 2 days, I will finish them up on the Wednesdays and Thursdays, but hopefully most of Wednesdays and Thursdays will be devoted to Q&A. There are 2 homework assignments due this week. It is 11 and 12. There will be 2 due next week, which are 13 and 14. All 4 of those are short compared to what you have seen before. So having 2 homework assignments should end up being about the same amount of homework work as you had in previous weeks. Sorry, my brain hit a speed bump. Let's try that again. So there is going to be 1 more small group activity. That small group activity I will hopefully be able to release today or tomorrow. And that I have extended the date for when it is going to be due next week. It's not going to be Tuesday and Wednesday as normal. You're going to have some extra time on that. This particular activity, I think, will be a little less challenging than some of the ones that you have seen previously. It is looking in depth at a particular pseudoscience idea using concepts of spontaneity and Gibbs free energy and thermodynamics, but it is a little less far afield than some of the things that you've seen in previous small group activities. There will not be a 6th one. What we are doing for the 6th activity slot in the grades is that I will take whatever your highest of the 5 that you've done is, and I will duplicate it as the 6th grade. So your highest grade, counts twice is the idea there. About the exams, I've announced this before, but just to make sure everybody's on the same page with it. The original plan was for every bit of material that we cover to be covered on 2 exams, a midterm and a final. I realized, however, several weeks ago, that it doesn't make sense to do that for the 4th midterm set of material because there's no time in between the 4th midterm and the final for you to use that time to learn the material again or learn it better, and it doesn't make sense to test you over the same material twice in the same period. So what I am doing instead is that the 4th midterm exam is going to happen. it's going to be released, I hope, Thursday of next week, but it will not be due until the Friday of the finals week. So you have a long time that you can work on it. There will not be a fourth part to the final exam. Instead, that fourth midterm will also count once you half the score as that fourth part of the final exam. And so, because each part of the final exam is worth 50 points. So we're going to take your fourth midterm, you'll take it once, and it will count for the midterm as the normal score, and it will count as half its score as the fourth part of the final exam. The final exam will therefore be in 3 parts, one each for the 3 midterms that you've covered. Each one will be, I will try to make it so that you can do it in about half an hour, but I will give you an hour for each one. They can be taken separately. Remember the redemption points policy in the class, which means that if your score on a part of the final exam, when you double it, to bring it up to a scale out of 100, is greater than your score on the midterm exam, then your midterm exam grade will be raised up to that doubled final exam portion score. That way, if you have learned material in between the midterm and the final and demonstrate that on the final exam, then your midterm grade goes up by that amount. It does not work the other way around, though. If your final grade is the grade on the portion of the final exam is lower than what you would get on the midterm, lower in terms of the percentage, half of the score, then your midterm exam grade does not go down. And it also does not work that your midterm grade does not become your final grade if your final grade is lower. It is simply the one direction. If your final portion is higher than the midterm, then the midterm grade goes up. That's it. Okay. Any questions on any of the logistics of that? Oh, I didn't say timing on the final. So the 3 parts of the final I expect to release to you guys on the morning of the Monday of finals week, and they will be due on the Friday of finals week. And so you can take them in any order you want at any time within that period that you want. Any questions on the logistics of all of that? Okay. I do want to as well talk a little bit about the cheating issues and Chegg in particular. I'm not going to spend a huge amount of time on this though. So the number of students that ended up going to Chegg and looking at answers for the 3rd exam was phenomenally large. A very large fraction of the class was doing this. This is a violation of the BSU policies on academic integrity and is a violation of my specific class policies. Let me make sure that it's clear what the distinction is between allowed resources and disallowed resources. Allowed resources are essentially anything except the specific questions that are on the exam. So if you go and find a similar question and you learn how to do the problem that's on the exam by looking at that similar problem, but then you still have to translate that knowledge to the specific question that is being asked on the exam, then I view that as you learning the material, and that's fine. No problem with that at all. The problem is when you look at at someone else's answer for the specific question that is on the exam. And the issue is that several people posted the specific questions from the exams onto Chegg, and a lot of students went and looked at those specific questions. That is disallowed. That if I had wanted you to have a key to even check your answers to make sure you were doing it right, I would have given you a key and obviously that is not the way any exam can test your knowledge of anything. So that is disallowed behavior. I am in the process of getting from Chegg through the Office of the Dean of Students a report of who posted these questions and reports of which students visited the pages. Many students have come forward already before I have gotten that report, and that is a good thing that students come forward, because that is taken into account when sanctions are applied. If you are in that boat and you have not come forward by the time that I get those reports, then you will have missed your window of opportunity to come forward and to receive an understanding of the in terms of the integrity that you're showing by coming forward. So consider that very carefully. I do not know when this week I'm going to be getting that, that report. A brief editorial comment that is simply my own personal advice on this. Chegg has developed a reputation nationwide as being a hotbed of cheating. It has developed this reputation because it does not have mechanisms in place to ensure that the questions that its experts are answering are not questions that are in the middle of an assignment or in the middle of an exam. And in many ways, there are certainly plenty of people who think that the business model that Chegg follows is kind of depending on students using it in unauthorized ways. Because of this growing national reputation of Chegg in this regard, BSU, I believe, is looking at a policy for towards Chegg specifically. And what I have heard is that the policy is likely to be an outright ban of its use. That policy is not finalized, is not in place yet, but I do know that there are faculty members around campus, and there are certainly faculty members in the chemistry department that look at simply having a Chegg account as being tantamount to an intent to cheat. I'm not one that goes that far. I believe that it is absolutely possible to use a service like Chegg and be honest in the way that you do it. However, given that there is this growing feeling about the dishonesty of how Chegg is typically used, it is my opinion, which I am sharing with you, that it is not worth it to be associated with Chegg by having an account there. There are other services that provide that can provide similar things to Chegg that do not have the sort of answering questions on demand kind of service that Chegg does. So Khan Academy, for example, has an excellent reputation, and there are other services, for example, that can handle the flashcard kinds of abilities that Chegg has that are that I've heard very good things about. So my recommendation is to use those other services instead of Chegg. All right. All of that aside, is there anything else logistical people would like to talk about before I move on to the content for the week? All right, so let us get going. I'm going to share my screen and we will see how well we can make this work. All right, and I'm keeping the chat box up, so if any of you have questions as we go along, please do put them into chat and I will try to address them as we go through. All right, so the main topic for this week is spontaneity, and by this we mean whether a reaction can happen or not. A spontaneous reaction can happen, a non-spontaneous reaction cannot happen. It's important to remember, though, that can happen doesn't necessarily mean that it will happen. So for example, it's a spontaneous reaction for a diamond to turn into graphite, but the kinetics of that reaction are so slow that it effectively doesn't happen over the lifetime of the universe. Now, in order to talk about spontaneity, we need to bring into sharper focus a concept we introduced some time ago, entropy. we described entropy as a measure of the disorder of a system, but we need to develop a more quantitative explanation of entropy to really understand what it is we're talking about. So we're going to start by thinking about a deck of cards as our analogy here. How many arrangements of the cards are possible? Well, the answer to that is 52 factorial. So factorial is indicated mathematically with an exclamation point after the number. And the idea of a factorial is you take the number, you multiply it by one less than the number, you multiply it by one less than that number, and so on until you get down to 1. And so let's think for a moment about why this is the right way to describe how many possibilities we have for the arrangement of a deck of cards. Well, if we pick the first card, it can be any of the 52 cards that are in the deck. When we pick the second card can be any of the 51 remaining cards that are in the deck. So for those first two cards, there are 51 times 52 possible combinations that you would get of the first card and the second card, and so on down until you get through all of them. So that is why the factorial is what gives us the number of possible arrangements of cards you could have. How big is that number? That number is absolutely enormous. It's trying to calculate right now. Take a look at that number that we have here. This is essentially 8 times 10 to the 67. So how many of these arrangements might we consider to be ordered? Well, if by ordered what we mean is that they run from ace to king, and so on, but maybe we allow the suits to be in any order we want, then there are 24 different ways to have this ordering. We could have spades, hearts, diamonds, clubs. We could have spades, diamonds, hearts, clubs, and so on. So there are, I believe, 24 ways to do that. So if we take this number, here, we'll take that number and divide it by, oh no, my program stopped. Let's try to recover that. If we take that number and divide by 24, then we find how many times, if we were shuffling the shuffling cards, we would how long it would take for us to expect to find randomly an ordered arrangement. So we had 52 factorial, and if we take that number divided by 24, we find that we have roughly 3 times 10 to the 66 times that we shuffle the cards, out of which one time we would expect them to be that ordered, to be ordered in the way we just described. How big a number is that? It's really hard to imagine it, but let's try. Let's see if we can find a way to visualize how unlikely it is that it would be for us to find that ordered arrangement by shuffling. So let's say that let's look at the Earth. We have 7.6 billion people on the Earth. Let's suppose that each person has a deck of cards and does nothing except shuffle it. Let's say that you can shuffle the deck once every second. How long would everyone on Earth need to shuffle their decks before one of them randomly turned out to be ordered? Well, it would be, I'm not going to go through the calculation here, but it would be 1.4 times 10 to the 49 years. The universe is only 1.4 times 10 to the 10th years old. Okay, so clearly we're not getting anywhere close here. In fact, if every star in the galaxy had 10 inhabited planets around it, and each one had the same population as Earth, and all of them were, and every person on all of those planets was shuffling cards, and if the same were true in every galaxy in the observable universe, and we were all shuffling not at the rate of once per second, but once every nanosecond, it would take 200,000 times the age of the universe to get an ordered deck once. Absolutely insane. Now, this is what happens when this is what we mean when we say that it is a spontaneous process for an ordered deck of cards when you shuffle it to turn into a disordered deck of cards. This is what we mean when it is a non-spontaneous or impossible process for a disordered deck to turn into an ordered deck. You're not going to take a disordered deck, shuffle it, and find that it happens to be in this ordered arrangement. It's not that it isn't possible in principle. It's that we can calculate just how unlikely it is. And that likelihood is so stupidly small that we can be absolutely confident that it won't happen. And that is with only 52 cards. If we're looking at a chemical system of maybe a mole of molecules, we're not looking at 52. We're looking at something like 10 to the 23rd. So what we're going to do now is develop these ideas for chemistry applications by looking at a simple system. We're going to look at a system that is going to model a droplet of ink that is dropped into a glass of water. Okay, and so each box that we have here is going to be a place that there can be a molecule. We're going to represent the molecules as these blue marbles, and wherever we don't have a blue marble, we have a water molecule. And I want to point out before we go into this modeling that we're about to do right here, what we're leading up to, if you've done the reading, is figuring out the size of W, which is the number of ways of arranging a system in these calculations. In the Newton problems that you've seen so far, probably if you've started working on this, you've been given values of W rather than having to calculate them. I'm going to give you a little bit of a sense of how to do those calculations to find W, but I will not be asking you to actually do that. I will not, the idea here is for you to see a little bit of where it comes from so that it makes, so that the pronouncements that we're going to make about what spontaneous means will make some sense to you, not from the, but not from the perspective of I want you to actually do the calculations that I'm just about to describe. Okay, so what we are trying to do now is we're looking at a simple model here where we only have 10 molecules and 3 of them are the dye molecules. And we want to know how many different ways we can arrange these molecules in the in this set of boxes. Well, we can take the first marble and put it anywhere we want. So we have 10 possibilities. We can take the second marble and put it into any of the 9 remaining ones. So 10 times 9. We can take the third one and put it into any of the remaining ones. Well, that's now 10 times 9 times 8. So we have 720 ways that we can put 3 marbles in here, except we've just overcounted. So if we, because the order that we put them in what we just did would matter. So if that's the first one we put in, this is the second one we put in, this is the third one we put in. If instead we put this one in first, this one in second, and this one in third, then that would get counted as a different way here. So we need to figure out for a given placement of 3 of the dye molecules, how much do we need to reduce our 720 by? Well, we can have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, or 3, 2, 1. So there are 6 different ways that we can get these molecules in the same places. So what that means we have to do then is we divide our 720 by 6 to get the total number of ways that we can have 3 dye molecules distributed in the glass of water that we're looking at. Each possible arrangement that we have is called a microstate. A microstate, so this is one microstate, this is a different microstate, and there are 120 of them. Now, if the question that we're looking at, though, is under what conditions will we have all 3 of these molecules right next to each other? So in this case, we would say that the droplet of ink has not dispersed among the various water molecules. In this case, the top one, we would say that in this microstate, it is dispersed. So how, of the 120 cases, how many of them can we have where all three are together? Well, here's 1, 2, 3, 4, 5, 6, 7, 8. So 8 of the microstates, we give it the label droplet. And the other 112, we call it dispersed. We say that it is not in a droplet. These descriptions that we have here, droplet and dispersed, we call macrostates. So a macrostate is a collection of microstates that share a property that we can measure as a measure from a macroscopic perspective. And in this case, we have many, many more dispersed states than we do droplet states. And so if we have a system where we have the molecules of ink and the molecules of water randomly jostling around because of the kinetic molecular theory, which says that molecules are in constant random motion, then what's happening is that over time, the system that we're studying is randomly sampling different microstates. And assuming that all of these microstates have the same energy so that there's no bias towards particular microstates, that means that 112 out of the 120 times, so if it samples a microstate every second, then we can sample all of them in 120 seconds. And so 112 seconds of it will be disordered, and 8 of the times it will be ordered, as in a droplet. So let's think now about how we determined these numbers, how we got up to the 120 that we have here. Well, what we did was we took 10 times 9 times 8. Well, one way we can describe 10 times 9 times 8 is 10 factorial divided by 7 factorial, because that is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. And we see that everything except the 10, 9, 8 cancels. Okay. And then we divided by 6, which turns out to be 3 factorial. And so what we are doing now is then dividing by 3 times 2 times 1. So if we have 10 boxes and 3 dye molecules, then what we are doing is saying 10 factorial divided by 10 minus 3, factorial, times 3 factorial. So if we have n boxes and m dye molecules, then what we have is n factorial over n minus m factorial times m factorial. So I'm going to turn this into a function. So we'll call it microstates because it's calculating how many microstates we have. Don't worry about the notation I'm using here. You're not going to have to reproduce anything like this. But if I now call my function with 10, 3, notice that we get the 120 that we calculated manually a minute ago. So this formula is working for us. So but a droplet, a bunch of water, we said this was going to be a glass of water with some dye molecules in it, but only 10 molecules is an awfully tiny glass of water. So what we're going to look at now is what happens to this number of microstates when we start to get to bigger systems. Let's say we have 500 of them and we have 5 dye molecules that are being dropped into it. We're looking at 1,000 million billion, 255 billion microstates at this point. But 500 molecules of water? Nope, that's not even, that's nowhere close to what we need to be at. In a drop of water, literally a drop like from an eyedropper of water, there are approximately 1.67 times 10 to the 21st molecules of water in it. So this number, trying to plug it into my function, will crash my computer. It would end up being too large. And this is a program that can handle numbers that are just ridiculously large. So I'm going to take a billionth of a drop of water. A billionth of a drop of water, we do microstates of that, 1.67 times 10 to the 12th. And we'll say that we have 100,000 dye molecules. Let's see how many microstates we have in this case. 1.6 times 10 to the almost 800,000. Remember our deck of cards example? Our deck of cards example was gave us a number of microstates that was less than 10 to the 68th. And even with that example, we couldn't get an unlikely arrangement of the cards in the lifetime of the universe. If we're looking at something like this, then thermodynamics is telling us, statistics is telling us that an unlikely event is so unlikely that it just will never happen. An example of this that might, and so this is why when we look at ink molecules that have been added to water, they disperse. And then you never see it go backwards. You never see them recoalesce into isolated droplets, just because the statistical probability of that happening is stupidly low, is insanely low. It was this understanding that led Albert Einstein to give this quote: "A theory is the more impressive, the greater the simplicity of its premises is, the more different kinds of things it relates, and the more extended its area of applicability. Therefore, the deep impression which classical thermodynamics made upon me. It is the only physical theory of universal content concerning which I am convinced that within the framework of the applicability of its basic concepts, it will never be overthrown." And what he's talking about is exactly what we just talked about. This explains why the air molecules that you have in your room don't, even for an instant, all randomly end up in the square foot corner in the upper left of your room. It's simply so, there's no physical law that says they can't move that way. It's that the statistical likelihood of them moving that way is so low that it, for all practical purposes, never happens. So unfortunately, numbers as large as we just talked about are very, very difficult to work with. I mean, 10 to the almost 800,000 is something that computers can barely handle at all. So instead, we're going to work with a related concept called the entropy. And let's look at the connection. So suppose I have 2 stacks of playing cards. The first has 4 cards in it. The second has 5 cards in it. How many arrangements are possible for the first stack? Well, 4 factorial. How many possibilities are possible for the second stack? 5 factorial. So then how many possible arrangements are possible for the pair of stacks? Well, it's going to be 4 factorial times 5 factorial. And so in the first case, we have 24. In the second case, we have 120. And so for the pair, we have 2,880. if we call this number of microstates W, we have a W for 4 cards, and we have a W for 5 cards, okay? W here stands for ways, as in the ways that you can arrange the system. What we have for the total number of ways is that the way total is W4 times W5. Now, but if we think back to other concepts in thermodynamics, like we talked about enthalpy, which is kind of a measure of the amount of energy that is in a system. If we have the energy of 1 cup of water and the energy of another cup of water, then the total energy for the 2 cups of water are added together rather than multiplied. We would like to be able to do the same thing with our entropy. So instead, but W doesn't do that. W multiplies them rather than adds them. So what we're going to do then instead of this is we're going to take the logarithms. So the natural log of W4 times W5 equals the natural log of W4 plus the natural log of W5. And taking the natural logarithm has the extra benefit of taking very large numbers and turning them into much more manageable numbers. So you've seen this already in the concept of pH or pKa or something like this, where you take numbers like 10 to the negative 14 and you turn them into negative 14. So using this natural log idea is a way to accomplish 2 things at the same time. One of them is to take stupidly large numbers and turn them into more manageable numbers. And the second is to make the quantity that we're dealing with, which is we're going to turn it into the entropy in just a moment, and make it act in the same way that other thermodynamic properties like enthalpy or internal energy act, meaning that they are additive when you add components together. The guy who figured this out and did it was Ludwig Boltzmann, this particular formulation that he came up with is so important that it's actually engraved on his tombstone, shown here. S, the entropy, equals K, the Boltzmann constant, times the logarithm of W, the number of ways of arranging the system. And here the logarithm is implicitly meaning the natural log, or ln, even though it's not written. I don't think they'd introduced ln as the natural log at the time this was written. So in practice, we don't tend to calculate entropy from W because the size of W is just too big to deal with. But talking about W helps us develop an intuition about comparing systems, which of 2 systems will have a higher entropy, and thus which direction a reaction will proceed. We know that a dispersed state of ink in water has a higher entropy than a state where the ink is clumped together, which means that if you put ink into the water, it will disperse. Similarly, gas molecules have more places that each molecule can be than the same molecules as a liquid. So if there's enough energy, a substance will be in the gas phase rather than in the liquid phase. So this leads us to the second law of thermodynamics, which says that for any spontaneous process, the entropy of the universe will increase. Delta S of the universe is greater than or equal to 0, meaning that the final state of the universe is a higher entropy than the initial state. So, now, if you thought calculating W for a small system was hard, try doing it for the whole universe. But fortunately, there's some tricks we can pull to make this problem a bit more tractable. For example, we can divide the universe into 2 parts: the system we're studying and everything else, which we will call the surroundings. Secondly, we can recognize that we don't need to worry about everything that's happening in the surroundings. If I have a reaction happening in a beaker on my lab bench, determining if that reaction is spontaneous or not doesn't depend on what's happening in my neighbor's beaker. It doesn't matter if she is even doing a different reaction than I am. That has no bearing on whether my reaction is going to be spontaneous or not. All we need to deal with is the interactions between my beaker, my system, and the surroundings. And in nearly all cases, what that means is that what we look at is the heat transfer. So let's think a little bit about what effect a heat transfer to the surroundings means in terms of the entropy of the surroundings. So if heat is released to the surroundings, then the surroundings end up with more energy that can be distributed among all of its molecules. And entropy in many ways isn't just about where the molecules are spatially in space. It's also about how much energy each individual molecule has. So if you have more energy available, then there are more ways to distribute that energy, and so the entropy goes up. So we're not going to go through the derivation of this, but the relationship is that for a heat transfer from the system, the change in entropy of the surroundings is minus Q over T. Now, let's also remember what Q is in a constant pressure process. So if we're doing this in a beaker, we're at constant pressure because the atmospheric pressure that's performing on it is going to be constant, the atmospheric pressure that's surrounding you. And under those conditions, Q equals the delta H for the process that you're doing. So we can now combine these ideas. So we have delta S surroundings here. We can plug this in, and then we can plug in delta H for the Q. And now we have something, an expression written here where the delta S of the universe is dependent on three things, and they all have to do with the system. You don't have to worry about anything that's going on beyond the system. So we have the change in entropy of the system minus the change in enthalpy of the system divided by the temperature of the system. So this now has taken what seemed like a truly impossible prospect of measuring the change of entropy in the universe and has turned it into something that we only have to worry about the system for. So all I've done is I've now brought that expression up here, and I've expressed now the spontaneous process inequality in this expression here. The delta S of the system minus the delta H of the system over T is greater than or equal to 0 for a spontaneous process. To get this into a little bit more of a familiar form, we're going to multiply through by negative T. Okay, so when you multiply through by a negative number, you flip the sign of the direction of the inequality. We now have this expressed in a more familiar kind of way. Since we are only dealing with stuff having to do with the system, we can drop the subscripts and just assume that delta H means delta H of the system and delta S means delta S of the system. And I'm just going to rearrange them, and we now have a relatively simple expression. Delta H minus T delta S is less than or equal to 0. This expression is so important that we give it a new name. We call it the Gibbs free energy, delta G. And so the spontaneity condition then is that if delta G is less than 0, which is what we see right here, the process is spontaneous, meaning it can happen, that the statistics are such that it is reasonable for it to happen. If delta G is greater than 0, then it is non-spontaneous, and therefore it is impossible for it to happen. If delta G equals 0, then it is spontaneous in both directions. Let me back up here for a moment. I'll come back to equilibrium. Delta G greater than 0 means non-spontaneous, meaning it can't happen. But the reverse reaction for whatever is written would have the negative delta G of what we had here. So the reverse reaction would be spontaneous. Now, equilibrium is when delta G equals 0, meaning that it is spontaneous in both directions. All right. So, the next thing to recognize here is that we talked about delta H being a state function. And as a result, we can apply Hess's law to it. Well, delta S, because your delta S in principle could be thought of as just relating to the ways, the number of microstates you have, W. That is also a state function. It doesn't depend on how you got there. And T is a state function, temperature is a state function, because it only depends on what is the actual temperature, not on how you got to that temperature. And so delta G is going to be a state function as well. And so for all of these, you can apply Hess's law. Now, I recognize that Hess's law is a topic that was introduced in Chem 111, I think very near the end of the semester when a lot of people had sort of tuned out by that point. So I'm going to do a brief reintroduction of Hess's law, and we will then talk a little bit about how it can end up being applied in to cases of delta S and delta G instead of just looking at the delta H cases. So what we have here, we're going to start by looking at a reaction. We have the burning of hydrogen to form water. And we have here the burning of, the reaction of carbon with water to form carbon dioxide and hydrogen. And so this is how hydrogen is produced commercially so that you could then use it as a fuel up here. Now we have a delta H of reaction for this reaction. We can also notice that carbon is a fuel. We can burn carbon to make carbon dioxide, and we can find the delta H of that reaction as well. And what we can notice is that there's a relationship between these numbers. We see that if we take the negative 393.5 minus the negative 483.6, we get the number for this reaction. Similarly, if we look at combining these top two reactions, we flip around the direction of the first one, and we add them together, we get the second reaction. And so what's happening is we take the delta H of the first reaction, we take the negative delta H of the second reaction, and we add them, and we get the delta H of the resulting reaction. So this is what I would describe as the chemical algebra way of expressing Hess's law, which says that the heat of any reaction is equal to the sum of the heats of reactions for any set of reactions that are in sum equivalent to the overall reaction. Now, there are other ways to view this same thing. So the way I like to do it most is what I call box notation. And so I've drawn a box around the reactants, I've drawn a box around the products, and now I can draw a box around these sort of intermediates. So we can have a reaction that goes this way, which is leaving the carbon unchanged, and it's basically burning the hydrogen and oxygen. And we have the delta H for that reaction, which is the reverse of this. We have a delta H for this reaction, where we're leaving the hydrogen unchanged and we're burning the carbon to form carbon dioxide. And the delta H for that reaction is the delta H for burning the carbon dioxide. And so now, whenever we want to go from here to here, we can do that by either of two paths. We can take the fast road, take the highway here just by one step, or we can take the scenic route, going this direction. So we go against this reaction arrow, so we have to flip the sign of the delta H for this reaction, and we're going with this arrow, so we have the sign be the same as the sign we have. And indeed, the negative of this plus the positive of this adds up to this. So whatever path you take, write the delta H's on all of the arrows, follow your path. If you're going against it, flip the sign, and you will always get the same answers. Why does this work? Well, it works because enthalpy is a state function, and I like to point this out by using altitude as an analogy. So let's say we've got a hiker that wants to climb a mountain. Well, there are many ways that a hiker can do that. She can climb straight up the side. She could take switchbacks. She could even get picked up by a helicopter and dropped off at the top. But in all three cases, her change in altitude is the same, even though the distance she traveled is different. So the distance traveled is a path function, but altitude is a state function. And so that's the general principle that means that allows us to say that Hess's law works, that any combination of reactions that we use will result in the same overall delta H. We can do it in the chemical algebra manner. We can do it in this box notation manner that I like to use. And we can also do it in sort of a graph state function method, where we look at where are the energies on a plot. And so we have the various components that are shown in the box notation. They have different energies. And we can see that we have one reaction here, we have another reaction here. And so going from here to here, we have that delta H that we are looking at. All three of these pictures are depicting the same concept, and that is Hess's law. Okay. Now, we are and I said that this was a function of Hess's law of enthalpy being a state function. Well, we had just determined that delta S, that entropy, is also a state function, so we can do that as well. And that Gibbs free energy is a state function, so we can use Hess's law on that too. Now, let's take a quick look at the Appendix G in your online textbook. And you will see here that we have delta H as a formation, which you use as part of your of using Hess's law. We have a delta G of formation, which does the same kind of thing for Gibbs free energy. And we have absolute entropies. Notice that there's not a delta in front of this. This is not an entropy of formation in the same way that this is an enthalpy of formation. This is an absolute entropy, an absolute value of the entropy of the system. So let's think about for a minute why that might be, why we might be able to have a reference point for this where we don't have a reference point for enthalpy or for Gibbs free energy. Well, if we think back to the Boltzmann expression for entropy, where entropy equals Boltzmann's constant times the natural log of W, imagine a perfect crystal with no atoms out of place at 0 degrees Kelvin, meaning that it has no energy of any kind. A perfect crystal at 0 degrees has only one way that it can be arranged. It has a W of 1. And what's the natural log of 1? 0. That is the statement of the third law of thermodynamics, which is that the entropy of a perfect crystal at 0 degrees K equals 0. Therefore, unlike the case of enthalpy, where we have to have a sort of reference point that we're comparing it to, why we have these are enthalpies of formation. They are a change associated with a reaction. For the entropy, we can say that the entropy of gaseous aluminum is 164.54 joules per Kelvin per mole. But we can still use these values in a Hess's law kind of calculation the same way that we would use the enthalpy of formation. Now, let me switch back over here for a minute. We had this expression here, delta G equals delta H minus T delta S. And remember that delta G is what determines whether something is spontaneous or not. If it is negative or 0, then it is spontaneous. If it is greater than 0, it is non-spontaneous. Well, this is expressing here a linear relationship of delta G with temperature. So if we have both delta H less than 0 and delta S less than 0, and delta S greater than 0, excuse me, then this term is negative and this term is negative. And so delta G will always be negative, meaning that the reaction will always be spontaneous. If, on the other hand, the delta S is negative, then this term becomes positive, which means that there is some temperature at which it becomes non-spontaneous. Below that temperature, it's spontaneous. Above that temperature, it is not. And we can do a similar analysis for cases where delta H is greater than 0. So with this in mind, it is generally a good idea when you are looking at these tables of thermodynamic properties to not use this middle column of the delta G, because these values are tabulated at a specific temperature. That's what this little degree sign means here, is that it's under standard conditions, meaning at 298.15 degrees Kelvin, or 25 degrees C is when this is calculated. The delta H's don't vary all that much with temperature. They vary a little bit, but not a lot. The entropies don't vary all that much with temperature. They differ a little bit, but not a lot. But we just saw that delta G does vary quite a bit with temperature. And so as a result, for the delta G's, you have to remember, am I looking at it at the right temperature or not? So, so my recommendation is that instead of calculating the delta G for a reaction from these standard Gibbs-free energies of formation, instead separately calculate the delta H of the reaction and the delta S of the reaction, and use then this expression in order to calculate the delta G for the temperature that you're caring about. Okay, there is one last thing I want to go through here, which has to do with another aspect of review of some of the Hess's law kind of material, because I have found this to be a point of very, very common confusion among students, and so I want to hit it a bit harder. So the issue is that a lot of people will don't remember or don't understand what is meant by this delta H of formation that we're looking at. And the problem comes in because they look at this as, well, this is the enthalpy of aluminum gas, or this is the enthalpy of aluminum sulfide solid. That is not what this is. This is a delta H for a reaction, for a very specific reaction. And so I want to go over that a little bit here. Let's see. So using my box notation, we have reactants going to products, and we have some kind of convenient intermediates, and we are going by an alternate pathway to get from reactants to products. And so the overall delta H is going to be the delta H for this process plus the delta H for this process, where we're paying very careful attention to the arrow directions that are being drawn here. And so the question is, how do we pick useful, convenient intermediates? Well, something we can observe is that every compound is made up of elements, which means that we can write a reaction, whether it's even possible to perform it or not. We can write a reaction that takes the elements that it's made up of and forms that compound. So water is formed from 2 atoms of hydrogen, 1 atom of oxygen. So we put 2 atoms of hydrogen and 1 atom of oxygen on the left-hand side, and we put them into whatever their standard state is at 25 degrees C, which is diatomic. And now we have written a reaction, which we can either perform or not, that forms 1 mole of the compound we're interested in. Similarly, we look at benzene down here. We have 6 atoms of carbon, so we need 6 atoms of carbon in standard state here. We have 6 atoms of hydrogen, so we need 6 atoms of hydrogen in standard state here. Any compound, even something as complicated as this, just by breaking it down into its elements, we can write this particular formation reaction. That is what those numbers are that are in that table. They are the delta H's for the formation reaction of the compound. And that's useful to keep in mind. So So I'm representing them here as delta H of formation of the compound. And so if we look at elements in standard state as this convenient intermediate, because we have the same atoms here that we have here, we know that our elements in standard state are going to be the same for the formation reactions of the reactants and the formation reactions for the products. So we then need to think about which direction the arrows go. Because we are doing a formation reaction, whatever compound we have here, we are going against its formation reaction to come to the elements in standard state. And then we are going with the formation reaction towards the products. And that explains why we have these signs that we do. Because we are going against the formation reaction of the reactants, we have a negative sign instead of in front of the delta H's of formation. And we have a positive sign in front of the delta H's of formation of the products because we are going with that arrow. So I know that a lot of people just memorize, oh, for delta H, what you do is products minus reactants, which is what this says, right? But that's because of the convention that we picked for the these formation reactions, that we are using formation reactions where we start at the convenient intermediates and we go to the reactants and we go to the products. And so when we take our scenic route through those convenient intermediates, we are going against the reaction arrow of the formation reactions for the reactants and with the reaction arrow for the products. That explains the signs. The thing is, though, so this is just going through an example here of doing that. And so I'm going to skip over that for a moment. The thing is, though, that is absolutely possible to use a different definition of convenient intermediates. So for example, in this reaction I'm showing you here, we are adding 2 hydrogens to ethene right here to make ethane. What we can notice is that all 3 of these compounds are fuels that we could burn. So what we could do instead is look at the delta H's of combustion of these, and those are easy to measure. We can put this in a calorimeter and measure this delta H of combustion very easily, which takes the compound, mixes it with oxygen to form carbon dioxide and water. Well, for formation reactions, we had the arrows going like this. But for combustion reactions, we have the arrows going the opposite way. So if we were going to use the delta H's of combustion, it wouldn't be products minus reactants, it would be reactants minus products, because we are going with this reaction arrow and we are going against this reaction arrow. So my recommendation is don't just memorize products minus reactants. Instead, draw yourself a very simple box diagram. Write an R for reactants, write a P for products, write an I for intermediates, and think for a moment about which direction the arrows go. And then when you follow your pathway, that will tell you whether it's products minus reactants or reactants minus products. Okay, so that is the bulk of the material for this week. That is the there is one topic that I didn't get to. I realized, however, that I didn't get to that topic in yesterday's class for the Wednesday class either, so I will be handling that extra topic separately on Wednesday and Thursday. And I'll send out a Piazza notification to everyone so that people know that they need to tune in for that extra bit of material. Let me open this up to questions for any of this material that we've gone over. Is there anything I can try to clarify? I know that there was a lot of material there, and I know that it was that I presented it rather quickly. Some of it was review, but I think also some of that review was in ways that are probably slightly different from how you have seen it presented before. So I think it was useful to go through that. Any questions? Yes, there are LA sessions today and Thursday from 3 to 4:15. Absolutely. So I am not hearing or seeing any questions. So either it was very clear or it was so confusing you don't know where to start. Just got to start on that homework, I think. Yep. Was delta G the only one affected by temperature? So that's a good question. So delta H and delta S do depend on temperature, but their temperature dependencies tend to be mild compared to the temperature dependencies of delta G. And so at the general chemistry level, we tend to ignore the dependencies of delta H and delta S on temperature. When you get up to physical chemistry, which is a junior senior level class, we will drop that assumption and we will take into account the effect of temperature on both delta H and delta S. But as long as you're not getting too far away from the temperature where the measurements were made, you're probably okay for both delta H and delta S. So, you know, most of these tables that you see are tabulated at 25 degrees C. And so if you're in these kind of, you know, -50 to 100 degrees kind of range, you're probably okay. But if you're looking at something like thousands of degrees, then no, it's not gonna be right. And I do want to reiterate that all of the sort of background that I did with the deck of cards and the boxes and the factorials and all of those sorts of things, the purpose of that was to get a sense for why we can be confident when we say that something is spontaneous or something is non-spontaneous, why we can say it with such extreme confidence, because the numbers are just so disproportionately ridiculous. It is not something that I would expect any of you to actually do calculations with. All right, well, I am happy to let folks go early if there are no other questions. So as I mentioned, there will be one more main topic for this week. I will go over it at the beginning of class tomorrow. I will also go over it at the beginning of class Thursday. So you would only need to show up to one of those two to get that. The remainder of both tomorrow and Thursday will be Q&A. I will take questions from Piazza and I will take questions live from folks in the audience. And yeah, we will get through this material. I expect to, as I mentioned, I expect to have the small group activity out maybe today, maybe tomorrow for all of you. Thank you very much, everyone.